All right, welcome again, everybody, to another episode where we learn Script, Bitcoin smart contract together. So in last episode, we talk about, pretty much the standard libraries. We talk about, for example, ellipse curve, and also, different signature schemes like, that enable the Oracle, say, Robin signatures. So another big one, I think I left out last time because it's kind of its own topic by itself. It's so-called zero-knowledge proof. So we also had a library over there that enables you to do this natively on Bitcoin. So this is usually regarded as something impossible, on Bitcoin before. And if you go around, have been in the so-called smart contract space for a while, has been regarded as the most complex, sophisticated smart contract out there in all over all blockchains. So it's kind of amazing that even Bitcoin can do this. So it just shows you how expressive the Bitcoin smart contract could be. It's not as limited as people usually think. So today, for today and probably next time too, I'm going to dive in this library. But before that, I need to get you guys to understand a little bit about zero knowledge, so-called zero knowledge proof. So before I get started, so how many of you have heard about this term, and what is your sense? What is this about? Anybody want to chime in? Okay, so what is in your mind? What is it roughly about?
So in my very brief understanding, it's something that can prove something else without disclosing the information about this something.
Exactly. Anybody else want to, comment on what's your impression of a so-called ZKP?
I know that it's used for performance in some blockchains to not spend much time on the complete validation and only send the proofs. So it will drastically reduce the size of information stored on the blockchain on most nodes.
Yes. So it's a so-called, we'll cover later, but it's called a ZK rollup. Yeah, what do you talk about? You just mentioned. Great. Yeah, sounds like you guys have some background, so that's easier. So on a high level, so what is a so-called zero knowledge proof? That's ZKP. So in a high level, as Domino's just mentioned, so you are proving you can prove some statement is true without disclosing the exact statement itself. So the canonical example is finding Waldo. I think that's a different name in Britain. I don't know the name, but I think it's North America, it's called Waldo. So the basic idea is you got a sea of people and objects. For example, in this picture, right, it's kind of like a ski resort, and you got the trees, you got all the people who go there skiing, and the task is to find this guy over in the sea of objects and people. Okay, so usually this is this has nothing to do with zero knowledge. But then what if, let's say, we convert this into like a kind of like a challenge game, right? So Alice claims to Bob, hey, I have found Waldo in this picture, but at the same time, I don't want to tell you exactly where Waldo is. Maybe I don't want to disclose this secret. Maybe I want to brag to somebody else. I'm the only one who can find it. Whatever, or we're betting on money on it, or whatever, for whatever reason. Okay, so if in the typical setup, right? So Alice can just point to this picture and pin at a certain point, and hey, this is the Waldo, the guy, right? And then Bob will be convinced. But here the difference is, can Alice prove to Bob that he identified the guy in this picture without giving out the secret location? Okay, so what do you think? How is this possible? The Alice is proving the secret knowledge, right? So I have the knowledge of Waldo, but I'm not telling you Bob. But somehow Bob can be convinced. Is this possible?
In this example, I think it's possible in one or two scenarios, but it's not ideal. Allegory to zero knowledge proofs, because for zero knowledge proofs, if I'm correct, you can prove it without waiting for some disclosure time in the future and without central trusted authorities. But with this example, I can only imagine one of the two possible scenarios. One of them require a third-party trusted authority, and the other require some delayed verification. With delayed verification, you can make a photo of the scene, encircle Waldo, and put this photo in sealed something, and then you will disclose it at the same time. And in third party, it's obvious you like Alice shows it to someone else, and then he confirms to Bob.
Okay, great idea there. Anybody else think this is this achievable at all? Sounds a little bit paradoxical, right? At the first glance. Okay, so
what,
okay,
to be able to prove you know where you?
Sorry. Yeah, go ahead.
To be able to prove you know where it is without revealing any more information.
Yes. So basically, Alice proved to Bob, I know where Waldo is in this picture, but I'm not telling you the exact location. And somehow Bob will be convinced. Is this possible?
Like how you've done it there with the paper.
Oh yeah, I'm like, yeah, I mean, let's blame me. I already put the solution here. So would you want to talk about this? How would you do it?
I think I know your solution, but it's not ideal too. So Alice can cut the world from this picture and show only cutted piece to Bob, but it does not prove that she does not download some picture from the internet without finding it in this scene.
So she cuts out a sort of a shape, the Waldo shape in the paper, and then puts the paper over the scene, yeah?
No. She cuts original Waldo, but without seeing other scene on only cutted version.
No, I thought she made a hole that's Waldo shaped and put a piece of paper, a very large piece of paper, over the scene.
No, she would only show to Bob the cutted version of Waldo. Assuming that she does not download it from the internet and only have this version of the scene, it will prove that she found it.
But by cutting him out, she's then revealing where he was. She can't do that.
No. She would not show original scene to Bob, only the cutted Waldo image. If, for example, they are locked in the same room and they have no smartphones, only the scissors, it will prove it.
Okay. Yeah, that's one way. Yes, that's actually interesting idea I've never heard of before. Yeah, I think that can work. So basically the idea is you are locked, both of them, they're locked in the same room and there's no internet or whatever, and there's only one picture over there. And then I think Alice just hides the picture and then
Alice would have to eat the photo afterwards, I think.
Yeah, I mean, cut it and then just show, Bob the picture she got, right? Because that's the only way she can get the picture. That's the only place, right? So in this way, you can convince Bob, right? And also Bob doesn't know exactly because she has destroyed the picture afterwards. Does this make sense? I think, this works.
I think this is exactly the same scenario, but you only cut the piece in the center of the, blackboard, and that way you don't have to ruin the original picture. So it's
yes. So it's one,
yes,
same idea. I'm saying one is kind of like reversible. You have to destroy the original. But the second way is like what Liam is saying. If I assume Liam has read the article somewhere, basically you get a big, gigantic, let's say a blackboard or something. You can cut the shape in the middle, just cut the shape, and then Alice moved behind the board, and then Bob is standing in front of the board, and then if Alice can move the picture in a way such that Bob can see through the hole, Waldo, then Bob can be sure, Alice know where it is, but at the same time, because the picture is hiding behind the board, Bob doesn't know anything about this location. So in this way, this is another alternative way to prove, in a zero knowledge sense. Alice knows where it is, but Bob doesn't know where it is. But Bob is convinced because that's the only way you can show through this hole, right? Because if you don't know, you cannot show me through this hole. Make sense? Yeah, I think it's really thinking out of the box today. So I've never heard about the first approach, but I think it works. But the only thing is the picture has to be somehow is at least is it's not totally destroyed, but at least you have been cut a hole. So it's not maybe you can put it back later or something.
But you do have to totally destroy it, otherwise you've revealed the information of where it was. So it must be destroyed completely.
Yeah. It has to be hid from Bob, because if Bob can see the hole, he knows where it is. Okay. Yeah, sounds great. That's a high level idea. Just from non-blockchain, just use case. Right? You have other ones you can find online, Alibaba's cave or whatever, or let's say you have two balls, and you want to convince they are different color to a blind person. You can do this also too. So you can Google online. There are many other non-blockchain usage cases, but since we are focused on Bitcoin, that's another I think this example probably everybody here knows. So when you spend a regular Bitcoin payment, so-called pay to public hash, you are actually proving you have the private key, right, corresponding to this public key or address, whatever, right? But then the problem is I cannot just send the private key, right, to the miners. What's the issue? If Alice wants to prove she possesses some coins, should why not Alice just send her private key to the miners? Then miners can check, right? Is this an issue?
Have access to all her funds.
Yes. So this is a very good use case for so-called zero-knowledge proof, right? Alice has to prove she knows this private key corresponding to this address or public key, but she cannot disclose her private key because obviously, right? If she just publicize the private key, anybody can take her fund, right? So this is done by so-called digital signature scheme, right? Specifically, we use ECDSA, but you can use a lot of other types of digital signature scheme. So in a rough sense, this is also a perfect use case of zero-knowledge proof. Make sense here? So you are proving some private key corresponding to a given public key, but you are not disclosing the private key itself. But also the miners or any third party having the signature, they can check you do know this private key, because otherwise the signature verification will fail. Make sense?
Yeah.
Okay. So hopefully these two are one in non-blockchain, the other in the blockchain sense, give you an idea, more concrete idea what zero-knowledge proof. Right. So now we are getting into more details. So now we talk about the high-level ideas, and then exactly how do we use this in our applications. So that's the key. We want to get a little bit into this today. So if you have been into the blockchain space, you probably heard about this term, zk-SNARK. So zero-knowledge proof is a pretty generic system, right? You have different ways to do zero-knowledge proof, right? It's like you want to compute, for example, the 2 to the power of x, right? You can multiply it x times, or you can do it, let's say, double and multiply, or even you can do bit shift. You have different ways to do the same thing. The same idea is here too. So basically, you have many ways to do zero-knowledge proof, but this way is very popular in the blockchain space because of a few properties it has. So one is, I'm not going to cover all the things, but here is the first S it stands for succinctness. So meaning, first the proof is very small. Usually in the term of like 100 bytes or even maybe a few kilobytes, but it's minuscule compared to all the other option stuff, right? Videos, pictures. This is very small because blockchain, right? Usually it's kind of expensive, so you want to have the proof very small. And also another thing is it's very easy to verify the proof once you got it. Okay, so this is succinctness. We make it very friendly to blockchain's use case. I think there are some other properties which I'm not going to cover today, but for our case, this is the succinctness is the key here. So in this specific type of zero knowledge, what does it prove? So basically, prove this statement. This function about a statement about this like a Boolean function. So this is you can think about this as a mathematical function. It has two type of parameters. One is x, one is w. So x is usually called is known to everybody, both let's say Alice and Bob. The prover. One is called the prover. You want to prove something, and the other part is called the verifier. Usually, one is called let's say Peggy. Usually called in a crypto literature, the prover, and the other one is usually called Victor. The verifier. So basically, the prover wants to prove to the verifier. She knows the secret. This one has to be secret input. That it is a secret that's not shown to the verifier. So both know the function and x, and then the prover trying to convince the verifier he knows the w, the secret input, such that this function evaluates to true, but without telling the verifier what w is. So for example here, right? This function, in the Bitcoin key instance, right? The function can be, I know this secret. This secret can be the private key, right? The function could be just the so-called elliptic curve multiplication, scalar multiplication, right? So the private key times the generator equals to the public key, right? So in this function, this function could be just, this is the public key, this is secret key, private key, and the function could be just, the public key equals w times the generator, right? So this is just one instance of, this is very generic, can be actually for almost arbitrary function. Here, you can prove this statement is true without giving out this w. I think this is a little bit mouthful, and I just pause a little bit here. Any questions so far? So the key takeaway here is like, usually when you prove something, it's more concrete. When you apply this specific zero knowledge proof protocol, it has to be something like almost like a mathematical statement. It cannot be say, hey, I'm proving you, today's weather is sunny, it's raining, right? It's not some kind of like it has to be some computation. It's hash, is a digital signature, or is the so-called discrete log or some given some number, right? It's not. You can think about it as a mathematical statement.
Is it possible to prove something that is off-chain?
Yeah, depending on what that off-chain, what it is. You can say, I know a secret, right? And this secret hashes to a given digest, right? That's possible. It can be off-chain or on-chain, doesn't matter.
First time when I heard of this zero knowledge proofs, it was one blockchain which claims that in the future it will be possible to like having email-less login to all the websites using only zero knowledge proof as your verification of your person.
As a person or as a login authentication?
So for example, you have account on the blockchain and you can use your zero knowledge proof to access every website in the internet in the future without providing them your email or your other data.
Yeah, that's possible. Even it's today, right? If you log into some crypto wallet, that's exactly how they do it. So basically, you have the private key, right? So you are pretty much there. You are doing the digital signature. Then you don't need the credentials to log in, the email, password, username, because you are pretty much just using the you are pretty much using the signature scheme there.
Yeah, but for now it only works with a website which are adapted to this scheme to the crypto wallet login. But they claim they could do something that it will work with all the websites, and I doubt it.
Yeah, if there's some kind of standard saying, hey, I want to have this authentication, saying you want to authenticate through like a private key, public key pair, then this can work. Yeah, I think that's how it works under the hood.
Okay.
Basically, yeah, you're proving you know the private key. Yeah, that's a good another. Yeah, Yeah, I think most people they just call it the digital signature, but you can think of it as one type of one use case for zero knowledge proof in this sense. Okay. So here I'm showing like different stages when you use some kind of zero knowledge. So in this sense, so basically at the beginning it's like elliptic curve, cryptography. You generate a pair of keys. Okay, so you have some random list here. This is you can think about this random list. So this f is this just function, right? So once you have the function, you add some random entropy there. You generate a pair of keys. Once it's a little bit similar to a public key, but there's a key difference. So this is called a proving key. This is called a verification key. Okay. So here, both keys should be made public. Okay, that's a big difference. So in the elliptic curve key pairs, right? The private key has to be hidden from public side, right? But in this case, both keys are visible to the public, at least to both the prover and the verifier. Okay. So once you have the pair of keys, what do you do? So this is the prover. This is a prover function. So the prover, what does it do? You take the proving key, the public input, and because he also knows the secret, right? So he can produce a proof. Okay. So this is what the prover does. And what the verifier does, the verification function here, what the verifier, it takes the verification key, the proof, and the public input, and run through this algorithm. It's going to say yes or no. If it's yes, it proves, without knowing W, it knows, it's sure, the verifier is sure, the prover knows this secret such that this evaluates to true. So if you notice the difference here, can anybody tell me what's the difference, for the inputs to the prover and the verifier? What's the key difference here? Is there something different here? Other than the keys, right? The keys is different. What else is missing from the verifier side?
Secret information.
Yes, exactly. That's where the zero knowledge, side comes from, right? Because if the prover just give out everything to the verifier, it's very easy, right? Anybody can check it. But then that's not zero knowledge, right? Because I have to know the secret, which is not the case, which is not good for our case, right? So that's amazing part.
Yeah. Why the verifier and the prover key should be different?
Oh, that's just kind of how the math work out, and also what's in practice. This thing is going to be huge, maybe like a megabytes or 100 megabytes, and this thing is very small. So usually this prover is run off chain, right? In the blockchain, context, the prover can be computational intensive. It can run through huge machines, maybe take hours, minutes, and this proving key is also very big. It can be like 100 megabytes or gigabytes, right? So the verification key is almost like a hash of this function. So it's very small, maybe like 100 bytes, a few hundred bytes, maybe kilobytes. So that's why you can afford to put both the verification and all the key itself onto the blockchain. The storage and the execution is both. This part is on chain. I think that's why this specific zero knowledge is very friendly to blockchain, right? Can you imagine? This is like gigabytes usually and runs minutes. So then most blockchain, even for us, right, for Bitcoin, it's very hard to put it on chain. Does this make sense?
Yeah, thanks.
Yeah, good observation. Anybody else? I think this is kind of like a very dense slide, so I want to make sure everybody's on the same page.
Yeah, as a suggestion, I think it will be cool if you could put like a snapshot of the previous picture with Waldo, and see, the analogies between what's the public input, what's the private input, the proof. I think
I see.
that can be more visible for.
Okay, makes sense. Yeah, so let's just let me reiterate why the example we see before here, right? So here in this sense, the function is for the public input, right? This can be address or public key, right? Just let's say the public key. So this is a private key, right? And what is this function? This function is, if you remember what we talked about last time, the elliptic curve. So if you have a private key, how do you derive a public key? Anybody? How do you derive the public key from a private key?
You produce it by some function.
You multiply the point for the scalar point. You multiply times a number, right?
A point, yeah.
I think it's
Point, yeah.
Some encryption.
So,
I don't remember the details.
Yes. So I think,
yeah.
Yes. So you basically you have if you have a secret key W, you just time it with the so-called generator G, right? And then you get X. So this function will be X equal to W times G. Make sense? That is good suggestion. I think next time I put an example here. It's more concrete. Okay.
Yeah, but also more visual if you use the Waldo picture. So, yeah. So like the public input is the entire picture, the private input is Waldo. I think that can be more, the proof could be like this, two stick together.
I see.
Something like that.
Nice.
But yeah. Or maybe both, maybe slides with both, but yeah, you make it a little bit visual.
Okay, great suggestion. I'll make that change afterwards. Okay, great. All right, so hopefully you get the idea here. So let's jump into a few of the use case in the that's using zk-SNARK in the crypto space. So I want to get some famous examples, and then we can. I think next week, I'm going to get a little bit hands-on at how you do this type of things on Bitcoin. So one of the biggest examples, I think this is almost made this zk-SNARK famous, is so-called Zcash. Okay, how many of you have heard about Zcash before, the cryptocurrency?
I heard and used it.
Okay, what's your impression of what is Zcash? What does it do?
Well, it should be like anonymous cryptocurrency, which can be not anonymous, not like Monero, but it's also a little bit more complicated. So when you use it by default, it's not anonymous.
Yes, great. So, we are here in Bitcoin, right? So the Bitcoin, when you send a transaction, regular transaction, you are selling from Alice to Bob, right? It's from sender to the receiver. And if you check on the public chain, right, a lot of information is revealed, right? The sender address, the receiver address, and the amount, right? So Zcash is the same thing, using the same so-called UTXO model. The coins are stored in UTXOs instead of accounts. You have a Zcash, but the only difference, all the three fields are hidden. They're almost like encrypted, you can think of. So you cannot see the sender address, you cannot see the receiver address, and also you cannot see the amount. Okay, you just see some like gibberish or like random, almost like random bytes on the blockchain when you check it. So in this way, they claim they can add, just add more privacy on top of Bitcoin, right? So this is their claim. We're not debating the claim today, but I'm just saying what they achieve. But let's say we have a blockchain, right? So what's the obvious problem here? What's stopping me from just, let's say, spending money that's out of thin air or doesn't belong to me or more than what I have, if everything is kind of like encrypted? You see the obvious problem here, right? Because everything is almost like encrypted, but then how does the miners check or validate this transaction, right? You see the problem? You guys?
Yes.
Okay,
And
so
I see it.
there is a problem because Monero is like completely hidden from everyone, and you still can verify that you're not spending somebody else's funds. So I'm not sure how it's realized under the hood, but they look like they've solved the problem.
yeah, at Zcash, it basically just uses zk snark. So that's what they use. So basically, you know, the sender has to somehow convince the miners, you know, hey, I'm sending the coins and this coins belong to me. This signature is valid, even though everything is kind of like encrypted. But then the miner still can check it. So that's a zero knowledge sense, right? I'm proving you, I know, for example, the signature, and this UTXO belong to me, but I'm not revealing you exactly what the signature is. It's almost like encrypted, right? So that's achievable using the ZK snark or zero knowledge proof, right? I'm showing you I have these coins, but I'm not telling you exactly, you know, which these coins are and what exactly the signature is. Kind of makes sense? We don't have to go to all the details today, like, because that's not a big topic, but that's how they do it. Okay. So that's a Zcash, and then on the right, how many people know this? What this app is?
It's Tornado Cash Mixer.
Say again.
Tornado Cash, probably.
Tornado Cash, exactly. Yes, and this has been made famous because it's being sanctioned by the U.S. government. You know, basically what it does. Anybody knows what Tornado Cash does on a high level?
I may be wrong, but as I remember it, it's basically Ethereum crypto mixer.
Yes, exactly. So the idea is, you know, Ethereum or a lot of other so-called account-based, you know, blockchains is there's much less privacy because you are always using one account. So the problem is, what if you want to, you know, almost like obfuscate your transaction history, transaction trail, right? You want to hide your trail. What you can do is, this is like a big mixer. So let's say 100 people, right? They both send one ETH, you know, one ETH. This is the base currency for Ethereum. Everybody says one ETH there into this so-called Tornado Cash smart contract, right? Every 100 people, all the 100 people each send one Ether here, and then later on, when they're trying to withdraw, they can withdraw the one Ether again out, but to a different account. So in this way, they're trying to, you know, obfuscate the link between the deposit and the withdrawal. But the critical problem here is, when I withdraw, how would I prove I've deposited into this before, right? So that's the biggest challenge here, because somehow I need to prove I've deposited, but without telling you which deposit coming, because otherwise you can link the withdrawal, right? Because that's the whole point for Mixer is, I don't want you to know, you know, which deposit is linked to the withdrawal later on, right? I could be the first one, but to deposit, but I could be the 50th to withdraw. The first one is requirement is I have to somehow prove to the smart contract I have deposit before, right? And at the same time, the smart contract cannot know which, you know, withdrawal corresponds to which deposit, right? And also the smart contract has to make sure I can only withdraw once, right? Because if I only deposit one Ether, if I can just keep, you know, withdrawing, I drain out the whole contract. I just take the money of all other 99 people, right? Which also doesn't make sense. So here it has a lot of challenges, you know, technology, and eventually it's also solved by so-called ZK snark technology. Okay, so here we are only talking about the tech, but we're not talking about the legal side of things. So this can be another talk, but basic idea is they also use the ZK snark to prove, you know, I have deposited before, but somehow you don't know which deposit it is. So that enables me to withdraw 1 Ether later. Okay. Any question about this?
Is it like 100% anonymous if you send funds to this Tornado Cash crypto mixer? Because, for example, in the Bitcoin world, for the mixers that I know, they are like 99% anonymous. But if someone really wants and have the technologies to analyze this thing, they still can track you. So is it the same with Tornado Cash?
It's the same with Tornado Cash, right? Because that's happened to all the mixers. It's only as good as how you are like hiding among a crowd, right? It's only good if the crowd is big, right? It doesn't make sense. You only have 2 people here using it. Then it's very easy to track, right? But if you have, let's say you have 1 million people, then it's much harder to track, right? It's like any other mixer. It depends on the pool size of all the, how many people you're mixing with, right? You're hiding in a crowd to say, right? Whether a small crowd or big crowd.
So
Make sense?
basically, big governments can completely undermine the security by like scaring off 90% of the people with sanctions, and they even don't need to like scare 10 remaining percent because they will be easily trackable, right?
Yes, that's one way. Or as the sanction does, is they just say, hey, nobody can interact with this contract at the contract level. So no, if you deposit, your fund is stuck because the miners, if they fall into the U.S. jurisdiction, they cannot process this transaction. So it's pretty much blacklisted their contract address. That's actually what happens in the real world. So a lot of people, the fund gets stuck because the transaction will be rejected when they try to withdraw.
Okay, thanks.
Mm-hmm. Anybody else? Okay, so let's go to the last use case here. I think we can continue. We can continue next time. So there's another very interesting type of games that's enabled by so-called ZK proof on the blockchain, which I think I'm very bullish about. So think about the blockchain, right? Everything is transparent, right? Because once you put the information on chain, everybody can see it. It's visible, right? You're not hiding any information. That's why you can do, let's say, CryptoKitties, or you can also play poker. Sorry. You can also play chess on chain, right? Because in those type of games, it doesn't matter. Everybody knows all the information about the game, right? But what if instead of playing chess, you want to play poker? It sounds impossible, right? Because in poker, we are not supposed to know each other's cards, right? And what's on the deck, what's the remaining cards? What are the remaining cards, right? Because if you know that, that's not the poker I play, right? And so you can easily cheat, right? So that begs the question: is it possible to play this so-called incomplete information games, right, or so-called hidden information games on a blockchain? You think about all the most popular games today, right? Civilization, World of Warcraft, those are all, or Counter-Strike, whatever. It all belongs to this so-called incomplete information games. You don't know everything all the time, right? So that brings a lot of strategy and game theory into the game. That's what makes this game fun, right? So that's the big question is, if we want to move all these kind of games onto the blockchain world, we can talk about what the benefits of what do people want to talk about. But let's talk about it today. Just assume, what if some people want to bring this kind of game and put it on the Bitcoin? Is this possible?
Well, it is possible if you will not like 100% put them into the blockchain and something will remain on central servers.
Okay, that's not entirely on. I'm saying that's like a hybrid, right? But I was asking here is it possible to play everything on its own chain?
Well, I guess with
yes, that's how this is made possible, right? for example, I put 2 examples here, which has people have been implemented on blockchain. So this is similar to poker. Anybody not played this game before? Heard about this game? Battleship? So everybody has played with it? Okay.
Yes.
That's good. So basic idea is, Alice playing with Bob, and they place the 2 phases. First one, they place a fleet into this coordinated grid, and then once they have finished the placement, and then each one guess to pretty much fire at the opponent's position. And if it's a hit, it's a hit. And then if a miss, it's a miss. And then whoever sinks all the opponent's fleet first, he wins, right? So it's easy to see. You can play this offline, right? It's very easy, right? Because you have this something blockage in middle, so you cannot see your opponent's fleet position, right? Because this is the whole point is you cannot see, right? But then if you move with the blockchain at the first glance, right? If you put it on chain, then I can know all the position here. I can just fire at your exact location. I don't even have to guess, right? But then the zero knowledge enables you to do is, let's say I don't put the information directly on chain. I just put the hash of the locations on chain. And then later on, when you fire at me, I need to produce a proof saying, hey, is this a hit or miss? I cannot cheat, right? I can convince you, the opponent, I'm actually, playing this game faithfully. I'm not cheating. It's a hit, it's a hit. I cannot say it's a miss. So in this sense, the zero knowledge is kind of amazing, right? You're putting the information on chain without disclosing, but then you can also make sure, nobody can cheat, right? Does this make sense?
Yeah.
Okay. Yeah, actually, we implement the zero knowledge battleship on Bitcoin, and we also have an interactive course. I think I'm going to post the link. You can go there and check it out. You can pretty much, it shows you from the beginning how to design a contract, and then how to interact with the wallet and front end to build a fully functional battleship. You can play it on Bitcoin today, which is the first. I think it's very cool. So this is I think this is a decent game. And then if you want to play, like a real massive online multiple player real-time game. So they have this game, originally designed on Ethereum. They have some other issues, but it's like almost like a space conquer game. So the idea is, it's a universe, and each player has a planet, and planet has some resource, and then if you have good resource, you can build a spaceship and explore the unknown universe, and then you can conquer them, the other planets, and so on and so forth. So the idea here is, the dark forest, right? The analogy from like a sci-fi novel is, it's like the whole universe is a forest, and different civilizations, they are trying to explore the universe, but because they don't know what the other civilization will do, they're trying to hide the information, right? Because what if this is like very aggressive civilization, and it's like thousands or even millions of years ahead of me, then if I give out my location, I'll be destroyed, right? So the game, the central scheme of this game is, I'm playing entire game on chain, but I cannot cheat. I can prove I have this position, I'm here, and also I'm not moving beyond speed of light. And you pretty much enforce all the game logic, but you are not disclosing your location. Which is also made possible by zk-SNARK. So it's very, very popular, and Dark Forest. So I mean, of course, this kind of UI is kind of like a primitive. It reminds me of like maybe 20 years ago game, but this idea is very sound. I think they are now, encourage a lot of other developers that are developing all kind of massive real-time multiplayer games on top of blockchains. So this is also very interesting development. I think I'm being following. I think we don't have to get all the detail, but the idea is you can actually build some kind of like a World of Warcraft, or even, let's say Civilization entirely on chain, everything is on chain, not only the state, but also the game logic. But at the same time, you can hide information. So that's what makes the game more fun, right? So I could imagine, if you have some even kind of a metaverse, right? Eventually, if you have a digital identity here, it's like the universe. You are only aware of your nearby information. You don't know the global entire universe information. But still, if you put all this your digital universe on chain, you can also enforce all the conditions, game logic on chain as well, because you can use something like a ZK Snark. Kind of makes sense here?
Yeah.
Okay, I think there's good enough information to get started. I think the next one, I think get a little bit hands-on to show you how to exactly do this on Bitcoin and in Scrypt. Okay, so any final thought for today?
No, thanks.
Okay, that's good. Yeah, I hope this is very interesting. I think this is one of the most, if not the most, interesting smart contract use case I could think of, and it's not pure Ponzi. So it's actually, I think this one could be one of the first, killer apps coming out of the smart contract, especially on Bitcoin. I'm very bullish on this. So if you guys have good ideas, we always have Zero Knowledge Hackathon coming. So it's great you guys can have some kind of games. Oh, somebody also built a Zero Knowledge based, Minesweeper. I hope you guys have played the Minesweeper before. Which is also a very cool idea, right? So basically, you don't have to trust the server. I assume you guys all heard about Minesweeper, right?
No.
Oh, Minesweeper is just a game. That's actually. Hopefully, you can still see my screen.
That thing from Windows, wasn't it? Yeah.
Yeah, you guys can see my screen? Browser?
Yeah.
Yep.
So we have the Zero Knowledge Hackathon. We have many participants, but then we have 10 finalists. But for Minesweeper, is this classical? Oh, maybe you guys are. I'm like too old,
Yeah.
I used to play this all. So everybody. Oh, okay, Minesweeper, yeah. So basically, the idea you have mines, and then you are exploring this, and if you hit a mine, you explode, you die, right? So this is a very good use case because if I put this on chain, I want to hide all these mines, right? Because if I know where the mines are, I can easily. This game is not it's not fun anymore, right? But somehow I still make sure, if there's a mine here, I can be proof. It can be proved. Also, not a mine also can be proved. I don't have to trust the server. Right? I can only just show me the proof. I can be convinced that this game is entirely legit and nobody's cheating, right? So many such examples. We can get into more details next time. And also some people like a poker, Texas Hold'em kind of thing. So also ZK Snake, you can play the game. You just there's some poison in the grid and you are playing the snake. You can prove to you whether this is safe grid or not. Yeah, it enables all kind of interesting, at least game in the game space. Very interesting and legit, I think. Okay, I think next time, maybe next time too, I'll also show you how to exactly this. So I think today is we can just stop here. Okay, sounds good.
Yeah.
Okay, thanks, man. Thanks all, and see you next week. Okay.
Bye.
Bye.
Yeah, thanks for that.
Thanks.
Bye.
Have a good one. Bye.
Bye.